kinds of outcomes can they have, and what kind of, particularly what kind of very energetic activities can they engage in. So to do that, I want to start out with a little bit of a review of how stars evolve, and you'll see that it depends very strongly on the mass of the star. So we can take a quick look at our sun, and if you just Google the sun and look for images, there are many different representations of our sun. Beautiful images taken with telescopes, as well as more fanciful artistic representations of the sun. Well, what do we know about the sun? We know, given how massive it is, the only way it can sustain itself against its own gravity, the only way it can prevent itself from collapsing due to its own gravity, is by having some energy source. And that energy source turns out to be fusion. And in the sun, it's currently hydrogen that is fusing into helium in the core of the sun. And the sun has enough hydrogen located in and near its core that it will be able to do that for about 12 billion years. And it's only about 4.5 billion years old so far, so we've got a while to go. We call it a main sequence star because it's well, just kind of chugging along burning hydrogen like most stars in the galaxy. As it evolves, it will eventually burn through all of that hydrogen in the core, and then a lot of interesting physics happens. When the core is no longer able to provide enough fusion reactions to support the star, there's a bit of a contraction in the middle, and that contraction process leads to heating, and the heating causes then the next layer out from the core to start burning. It gets the hydrogen in the next layer out gets hot enough to start burning. What's left in the core is largely helium at that point. It's the products from the hydrogen fusion. And you have to get to a much higher temperature in the core before you can start fusing the helium into more massive elements. So you go through a phase where a shell of hydrogen around the core burns via fusion. And it's a much shorter phase. And it's during that phase that the sun expands dramatically and fills up basically the entire solar system out to the Earth's orbit. And it's a red giant star in that phase. Now, once that shell of helium kind of burns itself out, the star rapidly contracts again to the point where it gets hot enough in the core that the helium can finally ignite. And at that point, you can burn helium in the core and some more hydrogen further out from the core. And you go through a couple of phases like this. And you can see they get shorter as you go along. And eventually, with our sun, it's really is an average-sized star for the galaxy. After a few 100 million years beyond that core, this initial main sequence phase, it's going to run out of things it can burn. And the problem is it just doesn't weigh enough to contract enough to get the core hot enough to burn anything more massive than helium. So it ends up with a core that's the products, the ash from burning helium, and that's carbon and oxygen primarily. And so you have a core in the star that's mainly carbon and oxygen surrounded by hydrogen helium envelope. That core takes on a special form, and the star settles into a white dwarf phase. Eventually the hydrogen and helium envelopes get shed, and you have just the carbon oxygen core sitting there. It's very hot but very small, and so that's why it gets called a white dwarf. And that's pretty much the end of the story for a star like our sun. And it's also pretty much the end of the story for most stars with a mass similar to our sun, anywhere from a little less than half the mass of our sun up to about 4 times the mass of our sun. If they're isolated stars, they don't have a companion, then once they finish fusion, they settle down as a white dwarf, and they'll have a very long lifetime gradually cooling off, and that's sort of their stellar afterlife. It's very peaceful and relaxing. Now, just briefly, less massive stars, less than half the mass of the sun, or a little bit less than that, they burn out their hydrogen but it turns out they're too low in mass to ever get hot enough in the core to even burn the helium. So all they're left with is a helium core. In fact, eventually, the entire star, all the hydrogen gets burned. The physics is a little different. The star has a lot of convection, so it's kind of like the star is boiling, and all the hydrogen and helium get mixed together until you burn all of the hydrogen. The thing is, the rate at which it burns is much slower because the star is so light. It doesn't need to burn very quickly. And so these low-mass stars can live for hundreds of billions of years. In fact, many of them are likely to outlive the galaxy or even the universe, depending on its ultimate fate. After they convert completely to helium, they've got some residual heat, but no new source of heat, really. So they just kind of glow dimly in the red and the infrared, so we call them red dwarfs. The vast majority of stars, about 85%, fall in this category. There's a lot more low-mass stars than there are high-mass stars. One of them has recently become very famous, a star called TRAPPIST-1, named after the telescope that first identified it. We now believe it has at least 7 planets in orbit about it, and those 7 planets all seem to be at a reasonable distance from the star, at which they might even have liquid water on their surface. Now that's way outside of my field of research. We need to get somebody in the seminar series talking about exoplanets in a future talk to talk about this. But TRAPPIST-1 and many of its cousins are fall in this category. Again, a very peaceful, relaxing, long afterlife. So that leaves us then with the high mass stars, the ones that weigh several times the mass of our sun or more.